One of the most important properties of water, one of the many important properties of water in terms of acid-base chemistry, is that it can behave as a base or as an acid. And we saw that in a previous slide. And it's not very good at either, but that means that it can, depending on what other compound it's against, it will behave as an acid or as a base. So when it's in the presence of an acid, water will behave as a base. So we have the example, let's say hydrochloric acid, any acid that will donate hydrogen ions to the water will generate the hydronium or hydrogen ion. Water in that case reacts as a base, accepting hydrogen ions. But water can also behave like an acid if you are in front of a compound that can accept hydrogen ions, and as its main behavior, water will be able to donate one of the hydrogen ions to the base. And we looked at this example, for example, with the molecule of ammonia. When you're looking at the reaction of ammonia and water, we said, one of the hydrogens of the water gets accepted by the molecule of ammonia. So ammonia behaves as a base, and the water behaves like as an acid. It donates a hydrogen ion to the ammonia and liberates the hydroxyl or hydroxide anion. Probably the most common way of calling it is hydroxyl ion, but in some places you will also seeing hydroxide. I'm going to ask you to stop the video and have a go at this exercise. Which of these equations have water behaving as an acid, and which of these equations have water behaving as a base? And as a little warning, there is a bit of a trick in some of them. So in what equations water behaves as an acid, in which ones behave as a base? Stop the video now, please. Okay, hopefully it was quite straightforward. The first two were quite straightforward because there are reactions that we have seen in previous slides. In this case, the molecule of water is donating a hydrogen ion to the molecule of ammonia. So here water is behaving as an acid. Sorry, I was starting to write base. So water here is an acid. In the second reaction, water and hydrochloric acid, water has accepted a hydrogen ion from the hydrochloric acid. So here water has behaved as a base. Now, examples C and D, what do you do with them? Do you say it was an acid? Do you say it was a base? The answer is none of them. These two are not acid-base reactions. They are what we call redox reactions, and we're looking at that in future videos. So here water is not reacting as an acid or as a base, because this is not an acid-base reaction. This is a redox reaction, which is a completely different type of reactions. So if you look at how did I know that? Well, there are quite a few ways you can know that, but if I look at the products, there are no ions. You know, if you transfer a hydrogen ion to another compound, you should have a positive ion forming, you should have a negative ion forming. The reactions C and D do not have positive or negative ions, and it's just reaction C is the split water into hydrogen gas and oxygen gas, not ions, compounds. And in the second reaction, in reaction D, you have water reaction with carbon to produce carbon monoxide and hydrogen. Again, there are no ions, there is no donating hydrogens or hydrogen ions or accepting hydrogen ions. So the last two were a trick, and it's something that we'll cover in future videos, which is redox reactions. Only the first two, you can identify the water as an acid or as a base, because only reactions A and B are acid-base reactions. Okay, so we were discussing that water can act as an acid or as a base. So it can donate hydrogen ions or accept hydrogen ions. That means potentially two molecules of water could react with each other in an acid-base reaction. But potentially, and they do, because one could donate hydrogen ion, the other one accept it. And that is something that is called autoionization of water, autoprotolysis of water. It's not exclusive of water, although the most important autoionization reaction we care about living in a water-based environment is water. It's not the only compound. Others can. Ammonia can do it too. But ask me if you are interested on that. But let's do the water one. Okay, so one molecule of water reacts with another molecule of water. And to not get confused, I'm going to declare that this molecule of water is going to behave like an acid and this one like a base. Okay, so the first molecule of water is going to react as our acid. What do acids do? They donate hydrogen ions. If that molecule of water donates hydrogen ions, it loses this H+. What you have is left is an OH and a minus. So the OH is there, and the minus is because the hydrogen has left the electron behind. It has left as a positively charged compound. Where has that hydrogen ion gone? To the second molecule of water, the one that I've declared that is acting as a base. So what do bases do? They accept hydrogen ions from the other molecule of water in this case. Instead of H2O, you have H3O, and you have a plus because it has not accepted a hydrogen, it has accepted a hydrogen ion, a hydrogen with a positive charge. So we call this autoionization of water. In a normal sample of water, we have a container with water. There will be a tiny amount of water that will have reacted with other molecules of water to liberate hydroxyl ions and hydrogen ions. This is what we call an equilibrium. It is an extremely displaced equilibrium. When you have a sample with water, most of your water will be covalent water. Water of this shape, floating with other molecules of water around, interacting with each other, but as water. A tiny minuscule amount will be what we call dissociated, autoionized. It will have reacted with other molecules of water to generate hydroxyl ions and hydrogen ions. And why do we care if it's a tiny amount? And I will show you how tiny it is in a moment. Because although it's a tiny amount, that number of molecules gives us our whole concept of what's an acid and what's an acidic solution and a basic solution. And more about that in the next slide.